For 500 years, human astronomy has followed a strict pattern of demotion. We mapped the Earth and realized it was one of several planets. We mapped the solar system and found it was a speck within a galaxy. We mapped the Milky Way and discovered it is a single data point among 2 trillion other galaxies. Every time we establish a boundary for everything, observation forces us to zoom out. Today, the boundary of everything is the observable universe itself, the sphere of light that has had 13.8 billion years to reach our telescopes. Popular culture treats the idea of spaces beyond this sphere, a multiverse, as a single speculative science fiction trope, a narrative device for comic book movies. But in physics, the multiverse is not a localized hypothesis. It is an unavoidable mathematical artifact. It emerges spontaneously when we push our most successful equations to their absolute logical extremes. 3 entirely distinct fields of modern physics dictate the existence of parallel realities. General relativity maps the geometry of gravity, quantum mechanics tracks the probability of subatomic particles, and cosmology studies the expansion of the early universe. None of these disciplines set out to invent a multiverse, yet all 3 independently break past the boundaries of our observable universe, forcing us to consider our reality is likely a localized anomaly within a vastly larger structure. To understand how these models command a multiverse, we have to drop the metaphors. We are going to trace the actual mathematics of these 3 frameworks, mapping them exactly to the point where they spill over the edges of our universe. Physicists do not guess at the existence of parallel realms. They construct equations that successfully predict observable phenomena, and then they refuse to abandon those equations when the variables yield counterintuitive results. The first of these mathematical spillovers originated with Albert Einstein. His equations of general relativity provided an impossibly precise map of how mass bends space and time. Because the mathematics so rigorously predict realities outside our own, the burden of proof has shifted in modern theoretical physics. The challenge is no longer inventing reasons why a multiverse might exist. The challenge is explaining why we don't see one. To see exactly where Einstein's equations break the boundary of our universe, physicists use Penrose diagrams. These are topographical maps that track the flow of spacetime, allowing us to trace the geodesics, the natural, free-falling paths of objects falling into extreme gravity. This diagram represents a standard, non-rotating Schwarzschild black hole. On this map, time flows upward. If an object crosses the event horizon, its geodesic is dragged inevitably forward in time, terminating in absolute destruction at the central point, the singularity. But the universe is in motion. Stars spin. When a spinning star collapses, it forms a Kerr black hole, retaining its angular momentum. That rotation physically alters the internal geometry, spinning the central point out into a ring singularity. If we trace a geodesic into this rotating black hole, the object crosses the outer event horizon and falls inward. But then it encounters a second boundary, the inner horizon. Here, the extreme rotation generates a massive outward centrifugal pressure, actively fighting the inward crush of gravity. The math dictates that this centrifugal pressure allows our free-falling object to avoid the ring singularity entirely. Instead, the geometry funnels the geodesic upward on the map, routing the object into the gravitational inverse of a black hole, a white hole. This white hole physically ejects the object, but because the original universe is mathematically located in the object's past, it cannot return there. The equations eject it into a completely distinct, causally disconnected region of spacetime. This mathematically mapped exit point is the relativistic multiverse. According to the strict rules of general relativity, the bottom of every rotating black hole contains a gateway to a parallel universe. But the math of general relativity does not operate in a vacuum. Mathematical possibility must survive physical mechanics. The physicist who designed this map, Roger Penrose, identified a fatal instability at that inner horizon. Any trace of matter or radiation falling in creates a current of positive energy, while the spacetime geometry creates a backward flow of negative energy. When these streams collide at the inner horizon, they trigger an exponential runaway effect called mass inflation. The resulting pressure would rival the Big Bang, collapsing the wormhole instantly. General relativity firmly demands that these parallel universes exist on the map, but the physical instability of the inner horizon acts as a cosmic sensor, ensuring they remain eternally isolated from us. If gravity requires a multiverse at the macro scale, quantum mechanics requires one at the micro scale. This emerges from the most persistent puzzle in particle physics, the measurement problem. Before it is measured, a subatomic particle does not have a definite location or spin. The Schrödinger equation describes the particle as a fluid wave function, a mathematical object existing in a superposition of multiple probable states simultaneously. The traditional Copenhagen interpretation asserts that the very act of observing this particle forces the wave function to collapse. The fluid probability instantly vanishes, leaving a single solid measured state in its wake. There is a massive structural flaw here. The Schrödinger equation perfectly describes the continuous evolution of the wave function, but it contains absolutely zero mathematical mechanism for a collapse. The collapse is an ad hoc rule inserted to make the math match our everyday experience. In 1957, Hugh Everett proposed a solution that removed the ad hoc rule. He argued that the math is completely unbroken because the wave function never actually collapses. When an observer measures a particle in superposition, the observer becomes entangled with it. The measurement forces the entire surrounding environment to split into orthogonal, non-interacting branches. In one branch, the observer records the particle spinning up. In another, they record it spinning down. This is the quantum multiverse. Every coherent superposition permitted by the mathematics is physically realized as a distinct parallel reality. In this Everettian framework, the universe does not roll the dice to choose a single destiny. All outcomes happen. Objective probability, what we call chance, is merely a localized illusion. It is just a measure of which specific branch an observer happens to inhabit at any given moment. The final pathway to the multiverse lies in the origins of our own. In the 1980s, cosmologist Alan Guth introduced inflation theory to solve glaring temperature uniformities in the observable universe. The theory postulates that fractions of a second after the Big Bang, a high-energy field drove space to expand exponentially, a violent, rapid outward burst that stretched out the initial irregularities of the cosmos. Inflation perfectly aligns with our observational data, but the mathematics governing it contain a specific quirk. The expansion field is eternal. Once inflation begins, it never stops everywhere all at once. Instead, localized regions of this high-energy field randomly decay to lower energy states. These regions drop out of the rapid expansion, cooling down to form isolated, stable bubble universes. Our entire observable universe is just one of these localized bubbles. While the space inside a bubble stabilizes, the high-energy field between the bubbles continues its exponential expansion. This rapidly pushes the pockets infinitely far apart, ensuring no two bubbles can ever physically interact. When cosmologists combine this inflationary framework with string theory, the implications compound. String theory provides a vast landscape of possible ways for physics to operate. As each bubble drops out of inflation, it can settle into a different configuration, generating a universe with entirely different physical laws and constants. This cosmological multiverse provides a strict mathematical basis for the anthropic principle. Our universe appears exquisitely fine-tuned for stars, planets, and biology, but it requires no miraculous fine-tuner. If there is an infinite landscape of inflating bubbles, generating every possible variation of physics, conscious observers will inherently only evolve in the specific bubbles whose laws permit biology to exist. We have three bedrock models of physics: general relativity, quantum mechanics, and cosmological inflation. By strictly following their equations, all three independently spill over the edges of the observable universe, predicting a multiverse. But this forces a confrontation with the core pillar of the scientific method, empirical observation. If we cannot cross a Kerr black hole's inner horizon, or observe an alternate Everettian branch, or travel across the inflating void to another bubble universe, is this actually science? The inability to directly observe these other universes forces a crisis in scientific falsifiability. A theory that cannot be tested is traditionally relegated to philosophy. To keep the multiverse within the realm of hard physics, researchers are adapting. If direct observation is impossible by definition, the scientific method must pivot to hunting for indirect empirical signatures, traces left within our own reality by the existence of others. This requires immense technological infrastructure, pushing our equipment to its absolute limits to measure the faintest fluctuations at the very edge of the observable universe. The hunt for the multiverse has become the ultimate test of modern physics, straddling the razor-thin line between theoretical mathematics and physical proof. Currently, the best hope for indirect evidence lies here. This is a map of the cosmic microwave background, the residual heat signature of the Big Bang. When researchers analyze this data, they find anomalies, most notably a massive cold spot that defies standard cosmological modeling. One working hypothesis proposes that this cold spot is an instance of gravitational scarring, a literal bruise in the cosmic microwave background, left behind when our expanding bubble universe bumped against an adjacent bubble in the inflationary void. Skeptics rightly point out alternative explanations. These anomalies could simply be imperfections in data collection, or localized phenomena entirely contained within our own universe, completely unrelated to external interactions. But the structural taxonomy remains. The deepest equations we have for gravity, for particle behavior, and for the birth of the cosmos do not map a neat, isolated universe. They demand an intricate, messy, and infinitely sprawling structure. The multiverse is the strict boundary condition of modern physics. Confronting it requires us to accept that our concepts of chance, physical law, and existence itself are merely local phenomena, tiny fragments of a much larger, unreachable whole.